Okay, so here is beginning of module 6, which is on decimals, like I said last week. Um, so this is a nice visual for representing how decimals work. We have a big block that means 1 unit, and we're going to split that into 10 rectangles and split those into 10 squares. So it takes 100 of the little squares, add up to the big square, or it takes 10 of the rectangles to add up to the big square. So we're just going to practice switching between our decimal representation and our pictures for now. We have 1, 2, 3 whole objects, and this is 6. 1, 2, 3, 4, 5, 6 of the rectangles and 8 of the little squares. Same thing here. We have no full one, and we have no full squares, but we have 9 of the little rectangles and 4 of the little squares. I think that it would probably be fair to say do the other two on your own. Um, so it does warn the above representation is great only if you have numbers that go to the hundredths position. You see, um, if we wanted to do like 3.281, okay, I have 3 big squares. I have 2 little rectangles. I have 8 little squares. Maybe I should have picked a smaller number than 8. We could continue and make little rectangles, but this just gets hard to see because they're so small. But like that's just the idea going down, is that you're always just taking the squares and breaking them into 10 equal rectangles, taking the rectangles, breaking them into 10 equal squares as you go down. Okay, so here are the names of the different places. The ones place goes to the left of the dot. This represents the first pieces we break the units into. So if we break into 10 equal pieces, they are tenths. We break those into tens and into we break those into 10 pieces, we get hundredths because it takes 100 of them to add up to 1 unit. We keep going, we get thousandths, 10 thousandths, and there's a nice mirror property between over here we have thousands. This is mirror image of thousandths, and 10,000s mirrors 10,000ths, with the ones sitting in the middle between all of the pairs that reflect each other. This dot, I know it feels like this dot is in the middle, but really the ones place is in the middle, and the dot marks where that is. All of the fractions will end in THS, or tenths, hundredths, so on. So this one here is in the thousandths place. This is in the tenths. This is in the ones, and I think you can do the rest yourself. The other hand, if I'm looking for the hundredths, THS means it's going to be smaller than 1. So I start off at, here's the ones, these are the tenths, these are the hundredths. The 6 is in the hundredths place. Okay. Same thing with 10 thousandths. You're going to look at this number. find out where that position is. It's going to be smaller than 1 because it says THS, and you can do that one on your own. Write the number in expanded form. So expanded form is one of these two things. They mean the same thing. This is a fraction, meaning we have one piece that is size 10 of them add up to a whole object. This means the same thing. That's why they have the same name. This is the tenths place. Tenths place in decimal form, but that's the same as 1/10. Well, a 1 in the tens place is the same as 1/10. These are the same word because they mean the same thing. Tenth means 10 of them to make up a whole. It doesn't matter if you write them this way as 0.1 or this way as 1/10. It's still a tenth, and it is the same value. So let's do this one. Well, yeah, let's do this one. So this one here we have, if you want to write the 0, you can. If you do that, it would be 0 and 84 hundredths. 0 and 84 hundredths. And the reason that it's that way is because the least significant digit is 4 here. Smallest digit is in the hundredths place. And you're just going to read that number between the dot and that digit as whatever that number would be without a dot, and then like you're gonna name what position that least significant digit is in. So this is 4. Oh, wait, we're just writing the number in expanded form. Sorry. This would be 8 times 1/10 plus 4 times 1/100th. I'm getting ahead of myself. There will be questions that ask you to write out the name of the word, and the computer is very picky on the homework. So I'll point out as much as I can to help you so that you can get through that. I guess this was foreshadowing. Anyway, so we have 8, that's in the tenths place, 4 in the hundredths place. And I'll wait until later to write more, um, write more words. We'll get to that problem when we get to it. Anyway, this here, this would be 50. I know I'm doing it again. I'm immediately starting to write the word. Okay. So this would be 5 tens plus no ones plus 1 times 1/10 plus no hundredths plus 6 thousandths plus 4 10,000ths. And we keep going. So, um, let's move on to the next problem. Okay. So this question says true or false? A digit in one place represents 10 times as much as it represents in the place to its right, and 1/10 of what it represents in the place to its left. Yes. So, for instance, 40 represents 4 times 10. This is in the ones place, and this is in the tens place. But it also represents 400 divided by 10. So, because this is in the hundreds place, and that's worth 10 times more than it being in the tens place. Okay, now we're going to get to the write the word thing that I jumped the gun on, but here we go. We want to convert this into a word, and we're going to use the same pattern as here. So there are 46 hundredths. Hundredths because it's 2 digits past the decimal point. This one is 24 and 900ths. When we see the dot, that's where we're going to put the word and. And separates the whole number part and the decimal part. Now, in practice, I say and a few other times when I say a number in words, but your computer grader will not accept ands in other places than right there where I said, where the dot is. So let me give you an example of that before we do one of these problems. If you're writing out this number, let me change it to this number. You're writing out this number, I would say this as 129, but the computer is only going to accept 129. No and there. So you have to be ready for that. So let's write the word name of decimal. The whole number is read, same as in section 1.1. The decimal gets replaced by the word and. The digits to the right of the decimal read the same as in section 1.1, except we add the place value of the name of the last digit at the end with THS. So we didn't do section 1.1 in this class because we are cohort 1, and therefore we start in section 3. But you can you can look at the lecture notes for unit 1, even though we didn't do that in class, by going to the module 1 in Canvas and downloading that section of the lecture notes. Anyway, let's do a few of these. This would be negative 1,057 and 1,002 ten thousandths. Aren't you glad that we created symbols so we didn't have to write out the word name for each number in our math? It's, the pro of abstraction is that sometimes you can make things easier to read by hiding some of the details in abstract concepts like placeholding. So it's, I think, a lot easier. We have 9 and 8 hundredths. 9 and we need this to land in the hundredths position. We need an 8 in the hundredths position. So we put a placeholder here, placeholder 0 to space that out correctly. This is our number. And I think this is a much clearer picture than that written out in words. Negative 46 ten thousandths. Oh, negative. We need 46, but we need this to be in the 10,000th spot. So this is 10,000ths. This is 1,000ths. This is the hundredths. This is the tenths, and we put the dot there. And this is the number we're looking for. You can do the other one on your own. The tallest mountain in the United States is Mount McKinley, which is approximately 20.31 thousand feet tall. Write that in standard form. So that would be 20,310 in standard form. So that's not too bad. Okay, consider the number line below. How would you label the tick marks? Well, if we're ending up at point 1 and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks to get across, I'm going to just divide point 1 into 10 groups like this. And there are my labels, equally spaced. Plot and label each of the following numbers on the number line. This one is here. Because 0.100 is the same as just point 0.1. Trailing zeros don't matter on decimal numbers. Same thing, this is going to be right here. 0 there. 0.072 goes a little bit past 0.07. And 0.038 goes almost all the way to 0.04. Which of the numbers is the greatest? That one. Smallest? That one. And we can tell because of how far left or right they are. We want to do the same thing here. Point, uh, 0.7 would be 0.9, 0.8, 0.7. Negative 0.3 would go here. 0.1 goes here. Wait, I skipped over. 0.3 goes over here. 0.1 goes here. And negative 1.8 goes negative 1, 2, 3, 4, negative 1, negative 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1. There we go. Labeled them all on that one. You can do this one by yourself. Let's continue. Determine which number is bigger by plotting each number on the number line. This is here. This goes here. So that one is bigger. Same thing for the other ones. I'll let you do those on your own. Well, maybe I'll do this one. So we have negative 0.13. So here's 0.1, here's 0.13. Then we have negative 0.31. So here's 0.03 and a little bit beyond negative 0.031. This one is the bigger number. Rounding digits works the same as when we were rounding whole numbers. Just have to know which decimal point we're rounding to. Nearest tenth, that's the tenths. So this is what we check. 3 means we round down. Negative 2.0 is what we round to. This one, tenths place. That's the tenths place. Here's the check digit. We round down. Negative 8.8. Let's do this one. Nearest whole number, we're rounding to here. So we check that. 4 rounds down. 1.0. Not too bad. Basic understanding of rational and irrational numbers. So we're going to convert decimals to fractions. Well, this here, this has 50 squares plus 7. This is 57 out of 100 squares. What decimals represented? 0.57. And the word is 5,700. Oh, where that came from. Okay, so We want to shade the values 0.65 in the grid below. Again, as at the beginning of the module, the tenths places represent the rectangles, the hundredths places represent squares. So we have 6 tall rectangles and 5 little squares. It's written as 65 hundredths, just like we did in the problem above, but with 65 instead of 57. We want to represent this as a fraction with a denominator of 100, so it's 65 out of 100, but cancel a 5 from the top to get 13, and from the bottom to get 20. This is the simplest form of the fraction in lowest terms. Same idea here. We're going to count how many digits we have past the decimal and put that many zeros and a 1 in front of it, and that's our denominator. The numerator is whatever's on top with the decimal point removed. That is a fraction that represents the same number as this decimal. Those are the same. I look and I see I can cancel a 5 from the top. That gets me 21. And on the bottom, I can cancel a 5, giving me 200. When you reduce these fractions, because the denominator is always a power of 10, you're always going to have the only numbers that you have to check are dividing by 2 and dividing by 5. So 1,000 divided by 5 is 200. That's my simplest form of the fraction. I don't have to worry about do the top and bottom both divide by 3 or divide by 5 or sorry, divide by 3 or by 7 or by 13 or whatever. I only have to look at 2s and 5s and products of 2s and 5s. So like maybe I can see, oh, I can divide by 20 here. And that'll save me a little time dividing by 20 instead of dividing by 5 and then 2 and then 2 again. But this number here, we have 4 digits past the decimal place. So I put 4 zeros and a 1 in front. That's my denominator. I remove the decimal point, 30771. And then I can divide this. I get 3 and 771 over 10,000. I know 2 doesn't go into that, and I know 5 doesn't go to that, so that doesn't reduce. Notice that the whole number part in the decimal form is also the whole number part in the mixed number form. So that's a nice feature. But this is our reduced number. 3 and 771 10,000ths is our reduced lowest terms mixed number. This is our lowest terms improper fraction. This would be 36 on top. When you remove the decimal point, all the leading zeros go away. On the bottom, we're going to have a 1 with 3 zeros behind it. I noticed that both of these are divisible by 2. I look a little closer and I can see they're actually both divisible by 4. So I divide the top by 4, and I divide the bottom by 4, and this is my reduced fraction. 2 and 5 don't go into 9, so I don't have anything more to divide by. I think you can handle the rest in that section by yourselves. Decimals are really nice for comparing which numbers are larger and which numbers are smaller. So we're just going to kind of go like a dictionary. We line up the dots and we say, well, which comes first, 3 or 3? If they're the same, we go to the next digit. Which comes next, 2 or 1? Well, 1 is smaller than 2, so we go like that. Same. 1 comes later than 0, so that means that 7.180 is bigger than 7.018. The directions get reversed when we have negatives, but we can still see that 7 is bigger than 2, so it would be this way if it were positive, and it's this way because it's negative. I want to put these numbers in order. First off, negatives will always come before positives, so those two come first. Uh, 6 is bigger than 0. So this is the big 60.62 is bigger than 0.06. But since they're both negative, bigger negative means uh, the least number of the two. 0.062 is going to be before negative 0.06. Now we look at our positive numbers. This one is the biggest because 6 is bigger than 0 and 0. This one is the next number because this is 0.060. This is 0.062, and 2 is bigger than 0. So we get 0.06, 0.062, and 0.6. These are our 5 numbers in order. Do the same thing here. Oh, now we have fractions though, so you might want to convert those to decimals. So decimal just really means that the denominator is a power of 10. We have 1/2. The decimal equivalent would be 5/10 because 2 times 5 is 10, and 10 is a power of 10. So I can just rewrite all these fractions as this is negative 0.5, 5/10, and this one becomes 0.5, and this one becomes negative 0.2, and this one becomes 0.2, because 1/5 equals 2 over 10, but 2 over 10 equals 0.2. We're doing this conversion. Now I want to put these in order. The negatives will come first, with negative 1 being bigger than negative 0.5. 1 is bigger than 0.5, so negative 1 is less than negative 0.5. Negative 0.3, negative 0.2, that's this one, then this one, then this one, then that one. Now we go through the positive ones. We have 0.2, 0.5, and 0.55. That's all of them. We're going to learn about perfect square roots. So we're just looking for, when we do this, we want to look for what number times itself equals that number. 11 times 11 is 121, so the square root of 121 is 11. That's all this symbol means, is what times itself is the thing inside of it. So for instance, with 1/4, square root of 1/4 is 1/2, because 1/2 times 1/2 equals 1 times 1 is 1 on top, 2 times 2 is 4 on the bottom. This leads us to an interesting thing. The square root of a fraction, like 9/16, is the same as the square root of the top of the fraction divided by the square root of the bottom. We can always just, if we have a fraction inside of a square root, we can split that fraction into, or we could split that square root into a top square root and a bottom square root inside of a new fraction. Like this one here, square root of 25 over the square root of 64. What times itself equals 25? 5. The negative sign gets dragged along for a ride. 8 times 8 is 64, so we get negative 5/8. This one here might be easier to see these two decimals when they're written as fractions. So this is the square root of 4/100ths, same as the square root of 4 over the square root of 100, which is 2 over 10, which we can rewrite as 0.2. That's fine. This one is square root of 121 over 10,000, which from earlier, we know the square root of 121 is 11. And we have to say, well, what's the square root of 10,000? Something times itself equals 10,000. I know 10 times 10 is 100. Maybe if I try 100 times 100, well, when you multiply 100 by 100, you get 0 in the ones place, 0 in the tens place, and then so that's 0 times 100 is 0, 0 times 100 is 0, 1 times 100 is 100, and so that is 10,000. That over 100, and there is our answer. This one, you're going to have to finish on your own, but I'll start it. So we want to find the square root of 2. We guess 0.14, and we get pretty close to 2. So the square root of 2 means what number times itself, itself, 2. And so we're going to pick some numbers, multiply them by themselves, and see how close to 2 we get. 1.4 gave us 1.96. That's a little less than 2, so we'll try something a little bigger. 1.5. Well, this gives us, when I multiply it, and you can feel free to use a calculator for this chart. I get 2.25, and that's too big. So I need something between 1.4 and 1.5. Maybe I try 1.45. That's halfway between 1.4 and 1.5. So I do that. Maybe I pull up my calculator, do it. Maybe I do 1.45 squared. I have a square button here on the calculator. That's 2.1025, which is closer, but still too big. So maybe I try something a little smaller. Maybe I try, instead of 1.45, I try 1.41. Get 1.9881. That's pretty close, but it's too small. So now I go up higher. Maybe I do 1.42. That's too big. 2.0164. And all I'm doing is, when I get a number that's too high, I pick something a little bit smaller. When I get something that's too low, I pick something that's a little bigger. And I do that until I fill out this table. So I'll let you fill out the rest of the table, but that's all I'm doing, is going a little bit bigger, a little bit smaller, until I get as close as I can. Does the square root function on your calculator claim this is that? I think so, yeah. Whatever number is displayed on your calculator, retype it and square it. So we'll just take the number that they have. Well, actually, no. I'll take the square root of. I get 1.414213. I have 5.6. They have it rounded there. If I type in 1.14, 1.414, 21356. I'm doing 5.6 because mine went longer and didn't round there. Theirs rounded to 3.6. But I'm going to take 5.6 because that's a little bit more. I'm going to square this, and I get almost 2. I got the answer I got because calculators round, and when we write this symbol, we mean the exact square root. The calculator displays this because this is a rounded answer. Calculators have a hard time with exact answers. So they approximate. They get as close as they can. So why do I think I got the answer I got? because the calculator is giving me an approximation, and when I type that approximation into the calculator to try and square it and get back 2, I am not squaring the exact square root of 2. I'm squaring an approximation that is close to the square root of 2. When I square that, I don't get 2 back. I get a number that's close to 2. So it's called error propagation. Happens when you round. Okay, let's keep going. Rational numbers are any number that can be written as a fraction where the numerator and denominator are integers. Irrational numbers are numbers that can't be written that way. So this is a rational number. This is an irrational number. Square root of 121 is nice because it's just 11 times 11 equals 121. So the square root is 11. Square root of 14 is not nice. 3 times 3 equals 9, which is less than 14. 4 times 4 equals 16, which is more than 14. So the square root of 14 is between those two numbers, between 3 and 4. Any square root of an integer that is not also an integer is going to be irrational. What I mean is that, like, the square root of 25 is 5. 25 is an integer, 5 is an integer. When I take the square root of 25, I get 5, and it's nice. They're both integers. On the other hand, if I try and take the square root of 24, I'm going to get something that's non-terminating decimal. It's an irrational number. So that's going to be irrational. This one's written as a fraction, so it's rational. This one, the square root of the top is 6, the square root of the bottom is 7, so this one is nice and rational. This one, it says it's a non-terminating decimal, so it's irrational. And you can do the rest on your own. The non-terminating, non-repeating decimal. This is a technique for approximating square roots. If I know all of my squares from the square of 1 to the square of 10, they go a little further. I can approximate roots. 1, 4, 9, 16, 25, 36, 49, 80, 68, 4, 4, 90, 81, 100, 121, 144. So I can use this to approximate square roots. I look and I say, well, square root of 5 has to be, well, 5 is bigger than 4, that's less than 9, so it's between, this is going to be between 2 and 3, and if I plug it into a calculator, I get 5 is 2.24 when I round it. The same as something squared equals. Same thing here. Something squared equals 65. It's bigger than 64, but it's smaller than 81. So this is between 8 and 9. And if I plug it into a calculator and round it, get 65 root 8.06. And you can do the other rows on your own. Okay. I think this is a good place to break the video. I'll upload more videos, but I want these in small enough chunks that they're not overwhelming. So that was module 1, module 6, section 1, module 6, section 2. And I'll continue with module 6, section 3 in a moment.